Although it's only one exercise, or it'll only be one question on the test, the Hell-Volhard-Zelinsky reaction, from a sort of Dr. Frankenstein perspective, is one of the most exciting reactions that you would learn this semester, because it lets you make amino acids. So let me emphasize that. It allows you to make any amino acid you want. You could make amino acids that already exist. You could make amino acids that don't even exist yet. And then you can use those, with other experiments. You can inject them into bacteria or into other organisms and see how it affects the metabolism or the proteins that those organisms make. And so it's really an exciting thing. This is a shocked face, by the way. It's like amazed and excited, because the ability to create an amino acid is really, really amazing. Really, the Hell-Volhard-Zelinsky reaction is almost the same thing as alpha bromination. The difference is that it adds, and here I'll say the HVZ, that's sometimes how it's abbreviated, the Hell-Volhard-Zelinsky reaction. That HVZ reaction adds a bromine to the alpha carbon, and here's the difference, of a carboxylic acid. Whereas in the alpha bromination, that added a bromine to the alpha carbon of an aldehyde or a ketone. So this HVZ reaction is really just alpha bromination for a carboxylic acid. Okay, now we're going to work through this and talk about how this happens step by step, and then I'll show you how you can make amino acids using this reaction, any amino acid you could think of, so far existing or not yet existing in the world. Let me show you the overall process that happens here. The main thing that happens is an alpha bromination, but carboxylic acids, the enol form for a carboxylic acid is not very stable, unlike with aldehydes and ketones. So the first thing we have to do is take whatever carboxylic acid you have and get rid of the carboxylic acid part. Because once you do that, once you get rid of the carboxylic acid, you can get the keto-enol tautomerism and then add the alpha bromine. The way you get rid of that in a way that it allows you to regenerate the carboxylic acid at the end is with phosphorus tribromide. Now technically you could also use thionyl chloride. Phosphorus tribromide is really the bromine equivalent of thionyl chloride, and I'll show you how the mechanism works for that in a second. But in the sense that it will replace the OH with a Br. Oops. So we'll see how that happens in a second, but the whole reason why we do that, why you want to do that, is because now we don't have the carboxylic acid OH anymore, and that's really what makes the enol unstable. So now the enol will be stable. You can do this sort of acid halide will exist in an equilibrium with an enol form. And from that, you can do the bromination, the alpha bromination. You have your sort of nucleophile there, so you can treat that with bromine, just like you'd treat the enol for an aldehyde or a ketone with bromine, and that gives you the alpha bromination product. And then the very last step is just to get rid of the acid halide. Just hydrolyze it. Treat it with some water. Water comes in and does a nucleophilic acyl substitution, and so you have the OH there again. So you'll notice that really these bookended reactions, this first reaction where you get rid of the carboxylic acid, and the last step where you regenerate the carboxylic acid, that's just accommodating that carboxylic acid as part of the molecule. And the middle part is really just the alpha bromination, like we've seen a million times. So it's nothing new. All of these things are things we've seen. But for the rest of this video, what I'd like to do is to take this reaction apart and talk in detail about how each of these steps happen. I just want this to be available to you in case you're interested, even though you wouldn't have to draw these mechanisms on this test. Before I do that, one last thing I want to show you, just in case you're ready to switch to a different video because you don't have the time, is I want to show you how you can make an amino acid from these things. Remember that anytime you have a halogen, the halogens open up the world to you. Halogens are leaving groups, and that means that you can use them to do either substitution or elimination reactions. And in this case, you would want to do a substitution reaction to make an amino acid. All you'd have to do is treat this with excess ammonia, that nitrogen version of water, and that ammonia molecule can come in as a nucleophile and do an SN2 reaction and kick the bromine off. Now, you'll remember this will not react to do nucleophilic acyl substitution here because this isn't a good enough leaving group, and this will be a base anyway, so it will steal the hydrogen off and make this an even worse leaving group first. You'll remember that when you wanted to make amides, you first had to turn this into an acid chloride before you treated it with excess ammonia. So if you leave it as a carboxylic acid, some of the ammonia is going to get used up as a base to steal that hydrogen away, but you have excess. So what's left over will not attack this carbonyl carbon. Instead, it will do an SN2 reaction here. So it'll sort of be like attack there, kick your leaving group off, and you have an amino acid. Now, this is called an amino acid because you have an amine with a nitrogen with all single bonds around it, and you have a carboxylic acid that are attached to the same carbon. So this is a special type of amino acid called an alpha amino acid. It's the most common amino acid in your body. And notice that whatever carbon chain you started with originally is attached in that amino acid. When you learn about amino acids in biochemistry, there will be a table of the 20 most common amino acids. All of them will have an amine and a carboxylic acid attached to the same carbon. The only difference between them will be what else is attached to that carbon. And you can see that using the HVZ reaction, you can just take whatever you want to be the R group attached to that carbon in between that determines what amino acid it is. Just make sure that that's on your original carboxylic acid. Any R group you can imagine, you can turn into an R group branching off of an amino acid. And then you can see how, if you inject that into an organism, how that changes the shapes of their proteins and how those differently shaped proteins affects different physiological processes in their body. So, really fascinating reaction, really useful from a Dr. Frankenstein sort of perspective, especially if you're doing research on protein chemistry. Okay, so now that we sort of have this background information, which I think would be valuable for anybody to know, I want to talk about this mechanism for those of you who are interested in this and want to see how this happens step by step. This is not something that would be on a test, so if you're limited with time, don't prioritize the rest of this video. But if you have the time, I think it's a really interesting thing. You'll see how stuff you've learned from throughout the semester sort of comes back and all builds on itself to create this beautiful pastiche. Okay, so phosphorus tribromide. Phosphorus is less electronegative than each of these bromines, and so it loses electron density to them. Each of the bromines becomes slightly negative. They steal the electrons for themselves, and the phosphorus becomes slightly positive. In other words, the phosphorus becomes a decent electrophile. At the same time, you have your carboxylic acid. And the oxygens in your carboxylic acid are slightly negative. Now, there are two versions of this mechanism. Because you have two slightly negative oxygens, either of those oxygens can act as a nucleophile. Either of these can act as a nucleophile to attack the phosphorus. If the carbonyl oxygen attacks, it's technically more correct, the mechanism, but it is so much longer. And it doesn't really shed that much more understanding. It doesn't give you that much more insight. So for the sake of brevity, I'm going to show you the mechanism where this oxygen in the carboxylic acid attacks. Remember that these lone pairs are allylic to this pi bond, so this is not a double bond, this is not a single bond. Both of these are something in between, and so this is really more symmetrical than they look at first glance. In any event, let's say this oxygen acts as the nucleophile and attacks that phosphorus. It could easily kick one of these bromines off. Bromine is a great leaving group. So you have nucleophilic attack, loss of a leaving group. This is an SN2 reaction. What you have after that step is really the same molecule you had before, but now this oxygen, well, the phosphorus doesn't have that second or the third bromine on there, but also this oxygen is bonded to three things. It's bonded to the phosphorus, that still has two bromines on it, and it's bonded to the hydrogen and to the carbonyl carbon. Because it has three bonds, that oxygen now has a positive formal charge. An oxygen with a positive charge is a great leaving group. And so the bromine that was expelled can come back and do a nucleophilic acyl substitution. So it attacks the carbonyl carbon, the pi bond breaks, you get your tetrahedral intermediate. That oxygen with a full negative charge is very unstable, so the electrons snap back down and kick the best leaving group off. And this leaving group with the oxygen with a full positive charge is even better of a leaving group than just the halogen. And so that leaves, kicks that group off, and that's how you get your acid halide. So you have that double bond to the oxygen there now, you recreated the carbonyl. The bromine is still attached to it, and this OH still is on the phosphorus with the two bromines, but that's a separate molecule now. That molecule goes on to live its own life, has its own adventures, its own epic saga. But meanwhile, we're left with an acid halide. So you notice that the effect of phosphorus tribromide is really just to replace the OH on the carboxylic acid with the bromine. So it has a similar role as thionyl chloride. Thionyl chloride replaces the OH with a chlorine. And if you remember the mechanism, it does it in a similar way. Thionyl chloride turns this oxygen in the molecule into a great leaving group. So it's similar. Okay, so now we've gotten rid of the carboxylic acid, so we can create this enol. If you have water in the beaker, then the water can sort of act as a base and steal this alpha hydrogen, slightly acidic alpha hydrogen. The electrons go onto the carbon there. So now we're doing the keto-enol tautomerism. So you have that allylic lone pair that's stabilized through resonance with the pi bond. And that is a resonance pattern. When you have an allylic lone pair, to draw the other resonance structure, you put that going toward the pi bond, and the pi bond electrons go away from the incoming electrons. So you end up with this enolate, ene double bond, very close to having an alcohol, but instead of a hydrogen you have the negative charge, so it's an enolate. And the hydronium that we created up here, that this water made, that comes back, oops, this hydrogen steals, or this oxygen steals one of the hydrogens from it, and the electrons go to stabilize the positive charge on the oxygen and the hydronium. So that's really just the keto-enol tautomerism mechanism that we talked about in the first couple of videos, or the first couple of videos in this chapter. So that gives us the enol. And you'll notice that's that second step, this step right here. Oops. So we had the acid halide, and now we have this sort of enol there. Once we have the enol, if you treat it with, we have a nucleophile in the molecule. That pi bond can act as a nucleophile and attack a bromine electrophile. So this is a lot like alpha bromination. As the bromine is very big, it's a very big atom, so it's very polarizable. As it knocks around randomly in the solution, when it gets close to this pi bond, it feels the negative charge of those electrons. All the electrons in the bromine go away from that, and so there's a slight positive charge in the bromine that can attract these nucleophilic pi electrons. All they need is a little push from the electrons above, and they attack the bromine, kick the other bromine off. Okay, so we're here. We almost have the bromine on the alpha position now. We just have to stabilize this by doing a proton transfer. So we could have water come in, act as a base, steal that hydrogen. The electrons go back onto the oxygen to stabilize the charge there. And so we've accomplished that middle part of the Hell-Volhard-Zelinsky reaction. We've put the bromine on the alpha position. So we've accomplished this part here. So first we replaced the OH with a bromine, and then we did the keto-enol tautomerism. That gave us the alpha carbon nucleophile, which could attack the bromine electrophile to give us the bromine on the alpha carbon. So now we just add water and do hydrolysis. And this is just going to hydrolyze the acid halide. So this is a standard nucleophilic acyl substitution reaction. So the water comes in, that attacks the carbonyl carbon, the pi bond goes up, you get your tetrahedral intermediate. You would stabilize that nucleophile. So another water molecule can just do a quick proton transfer so that it isn't a good leaving group anymore. Oops, and this oxygen has a full negative charge. So and then that negatively charged oxygen comes back down and kicks the bromine off as a good leaving group. So that you're ultimately left with the same carboxylic acid you had at the very beginning. You just have this bromine on the alpha position. So notice this OH here becomes that OH there. And that's your last step in this mechanism. So this last step here, with water, you just do a nucleophilic acyl substitution, replace the bromine with an OH. So overall, the change, if you ignore these different steps and you just look at the beginning and the end, the original molecule and what you wind up with at the very end, there's only one difference, and that difference is the bromine on the alpha carbon. So the Hell-Volhard-Zelinsky reaction puts a bromine on the alpha carbon, and it's really profoundly significant because once you have that, you can do an SN2 reaction with ammonia and create an amino acid, which is really amazing. So I wanted you to see that mechanism. In the exercise we're going to do in the future, we won't draw this mechanism again, but I wanted it to be available to you so that it didn't just seem like black magic. That you could see that this reaction is related to all the stuff you've learned this semester so far. So in the next video, in the next couple of videos, we're going to look at this reaction, the Hell-Volhard-Zelinsky reaction, or the HVZ reaction, from the perspective of synthesis.